The Cummins Big Cam was a titan of the road, known for its raw power. But what if a crucial internal change, meant to refine its operation, actually turned it into a ticking time bomb? By the mid-1970s, Cummins faced a challenge it couldn't outmuscle: tightening federal emissions regulations. The Environmental Protection Agency, established in 1970, was raising the bar for cleaner engines, forcing diesel manufacturers to look beyond just power and reliability. Now, engines had to run cleaner as well.
Shall we surrender to our surroundings, or shall we make our peace with nature and begin to make reparations for the damage we have done to our air, to our land, and to our water?
For Cummins, this meant adapting their proven NTC 855 engine, which had become a backbone of American freight since its introduction in the late 1960s, powering everything from long-haul Peterbilts to heavy vocational trucks. Designed before emissions were a regulatory concern, the 855 risked obsolescence as new standards loomed. Cummins engineers needed a way to meet these requirements without sacrificing the performance truckers relied on. Meanwhile, competitors like Detroit Diesel and Caterpillar were debuting new models and technologies aimed at improving fuel efficiency and meeting emissions demands in the wake of the 1973 oil crisis. The pressure to innovate was intense, so Cummins got to work on a solution, one that would allow them to retain the rugged bones of the 855 while modernizing its behavior. Their answer was deceptively simple in name: the Big Cam. But as the industry would soon learn, this wasn't just a bigger camshaft. It was a total shift in how diesel timing worked. To meet emissions requirements without overhauling the entire NTC architecture, Cummins engineers reimagined a key component: the camshaft. By increasing its overall diameter and enlarging the injector lobes, they enabled the engine to handle higher injection pressures and achieve more precise timing. This substantial upgrade is what earned it the name Big Cam, referring to the camshaft's increased size and capability. It allowed for more precise timing and higher injection pressures, improving emissions performance without requiring a radical engine redesign. This single change turned the camshaft into a more intelligent part of the combustion equation. With this redesign, Cummins could refine their pressure-time fuel system even further. Unlike some competitors, Cummins' PT system used camshaft-driven injectors with fuel delivery controlled by both pressure and timing, setting it apart from unit injector systems used by others. The larger camshaft allowed engineers to achieve more precise injector timing and higher injection pressures, optimizing combustion to meet stricter EPA standards. But even that wasn't enough. While emissions and fuel economy had improved under lab conditions, the engines were still dirty during startup and idle. White smoke, rough idling, and excess nitrogen oxides at light load threatened the entire Big Cam program. That's when Cummins added step timing control, or STC, a hydraulic system that used oil pressure to automatically adjust injection timing through specialized tappets and oil passages. At idle or light throttle, the system advanced injection timing automatically to reduce white smoke and improve cold starts. Under heavy load, it reverted to standard timing for optimal performance and emissions control. The beauty of the design was how seamlessly it adapted. No electronics, no driver input, just pressure-driven logic baked into the engine itself. It was clever and compact, essentially a form of early variable timing using only oil and fuel pressure. No wires, no sensors, and no need for driver involvement. In theory, it was brilliant. In practice, it introduced a hidden layer of complexity to an engine trusted for its predictability. The system's core component was the hydraulic tappet, which contained a small oil cavity and a spring-loaded check valve. When the engine operated at low oil pressure, such as at idle or light throttle, the valve remained closed and timing stayed at its baseline setting. As engine oil pressure increased with RPM and load, the valve opened, allowing pressurized oil into the tappet. This oil pressure advanced the injector timing by several crank degrees, optimizing combustion for different operating conditions. It was a clever workaround, but the system had two key weaknesses: oil contamination and mechanical wear. Even minor impurities in the oil could clog the STC valve or damage its sealing surfaces. A sticky valve could prevent timing from advancing at idle, leading to rough cold starts and smoke. Or, if stuck advanced, could keep timing too far ahead under load, increasing cylinder pressure and causing hard starts, knocking or elevated EGTs. Cummins designed the valve to be self-regulating, but in the real world, trucks didn't always get perfect maintenance. A bit of soot or sludge in the oil was all it took to throw off the system. Then there was tappet wear. The STC tappet, with its internal cavity and spring, was more complex than standard lifters. Over time, repeated heat cycles could weaken the spring or cause the check valve to stick, especially if oil quality was poor. Unlike a regular tappet, which might fail with obvious noise or lash issues, the STC tappet could fail quietly, often causing subtle power loss, rough idle, or fuel economy dips that were difficult to diagnose. What made things worse was how little information was available outside Cummins service networks. While Cummins provided service documentation, many independent mechanics were unfamiliar with the system and often didn't even know it existed. And because the tappet was located beneath the rocker cover, diagnosing a faulty one required removing the top-end components, something few shops were willing to do without clear symptoms. As a result, fleets started misdiagnosing the issue. Bad injectors, fuel pump problems, cam wear, even cylinder scoring. In reality, a single faulty STC tappet could throw off the timing for its cylinder, leading to performance issues that were often misattributed to other causes. There was also the issue of tuning. Mechanics who were used to advancing or reducing timing manually sometimes fought against the STC system without realizing it. They'd adjust the cam gear or PT pump, not realizing that the STC system would alter injection timing under certain conditions, sometimes counteracting their manual adjustments. And then came the deletions. Shops began offering STC delete kits, replacing the hydraulic tappets with solid ones and locking timing in place. While this removed the system's emissions and drivability advantages, it restored predictability and reliability for many fleets. For some fleets, that trade-off was worth it. STC was one of Cummins's boldest mechanical innovations. It worked well when maintained properly, but outside of well-trained service networks, it became one of the most misunderstood systems ever installed on a Class 8 engine. And that legacy would shape every generation of Big Cam to come. When the Big Cam launched in 1976, Cummins positioned it as a quiet revolution, emissions-ready, more efficient, and just as rugged as the NTC 855 it evolved from. And at first, it lived up to the hype. Drivers noticed the difference immediately. Cold starts were faster. Smoke at idle was dramatically reduced. The engine felt smoother, especially at lower RPMs, where older 855s sometimes stumbled. Owner-operators praised the improved throttle response, while fleet managers appreciated the noticeable fuel economy improvements reported on line haul runs. Under the hood, the Big Cam remained true to the formula that made the NTC legendary. It kept the same displacement, 855 cubic inches or 14 liters. It was still a 6-cylinder inline layout with a 5.5-inch bore and 6-inch stroke, a long-stroke design ideal for low-end torque. It ran a direct injection system paired with Cummins PT fuel system and operated under a 14:1 compression ratio on most builds. Output varied depending on spec. Some fleet engines were rated as low as 290 horsepower, while heavy-haul versions climbed to 400 horsepower and up to 1,400 pound-foot of torque in later models, with peak torque typically arriving between 1,200 and 1,800 RPM. It seemed like everything a working truck needed: brute force, high reliability, and better efficiency. Trucking publications gave it favorable early reviews. A 1977 write-up in Diesel Power praised the refined manners of the engine compared to its predecessors. Cummins had managed to introduce emissions improvements without obvious added complexity, at least on the surface. And that was the problem. Underneath, something new was happening, something that most people didn't understand. As trucks racked up miles, strange symptoms started appearing. Engines that ran perfectly during highway pulls began acting up at idle. White smoke, inconsistent throttle, and minor power dips crept in slowly. Some drivers noticed the changes, others didn't, until fuel bills started rising or performance fell off a cliff. Shops did what they always did: checked fuel pressure, adjusted timing, rebuilt injectors. Some replaced PT pumps altogether. Others dove deeper and replaced cam followers or valve train components. The problems kept coming back. Very few knew the engine had a hidden variable timing system, and fewer still understood how it worked. That disconnect became a growing problem. Mechanics who had worked on NTCs for decades were now chasing ghosts. The Big Cam used the same fuel system, the same overhead setup, and the same basic block architecture. But internally, it was a different animal. The step timing system introduced a dynamic element that didn't leave physical clues. There were no fault codes, no clear wear patterns. Just vague, recurring issues that didn't match any familiar failure mode. Some fleets tried to adapt. A few high-mileage operators began changing oil more frequently, thinking contamination might be the issue. Others pulled engines early and swapped in NTC components, eliminating the problem by reverting to older tech. In the aftermarket world, rumors started circulating. The Big Cam ran great, until it didn't. That reputation followed it. Some diesel techs began advising against it. Others swore by it, claiming the failures were always due to poor maintenance or neglect. The truth was somewhere in the middle. The engine still looked like the proven NTC, but inside, Cummins had unknowingly built a ticking time bomb, one that wouldn't explode, but would quietly undermine the Cummins reputation. The early complaints about STC didn't stay quiet for long. Within a few years of the Big Cam's release, Cummins dealers across the country were dealing with a wave of customer frustration. Trucks that should have been reliable were coming back with strange complaints. And worse, mechanics couldn't always pinpoint the cause. The core problem wasn't that the system broke dramatically. Small issues like a bit of sludge in the oil or a worn valve in the tappet could trigger unpredictable symptoms. Many independent shops unfamiliar with the STC system often blamed other causes, including driver behavior. As the warranty claims stacked up, Cummins had a choice: abandon the Big Cam concept or try to fix it in place. They chose the latter. What followed was a rapid-fire sequence of revisions, each one a patch, a refinement, or a course correction. The original 1976 version, later dubbed Big Cam 1, introduced the enlarged camshaft and, on many models, the new STC system. However, it retained the earlier oil channeling and smaller cam bushings, which would later be improved in the next version released just 2 years later. Big Cam 2 arrived in 1978, featuring improved oil flow and larger cam bearings to reduce wear. Some internal components, including tappets, were updated for better durability under varying oil pressures. It was an improvement, but not a cure-all. Engines that saw long idling times or poor oil maintenance still suffered. By 1983, the company released Big Cam 3, which introduced top-stop injectors, simplifying the process of setting valve and injector lash. It also featured pulse manifolds to improve exhaust flow and help lower emissions. The Big Cam 3 was widely considered the best balanced of the series. Then came Big Cam 4 in 1985, the final major revision. The most noticeable external change was the move from 6-bolt to 4-bolt valve covers. Internally, it featured updated oil galleries and timing adjustments aimed at meeting stricter emission standards and improving reliability. power ratings were pushed to their limit, with some engines exceeding 400 horsepower. But emissions rules were tightening and mechanical systems had reached their limit. Throughout these revisions, Cummins never directly acknowledged STC as the source of the issues, but many of the changes suggested efforts to address its challenges. What began as an elegant solution became a moving target, with each generation attempting to address weaknesses without sacrificing performance. But by the late 80s, it was clear that meeting new emissions and reliability standards would require electronic timing and diagnostics. The Big Cam had carried Cummins through a critical transition, but it had done so at a cost. As the Big Cam aged, Cummins dealers weren't the only ones hunting for answers. Independent shops and fleet technicians, tired of chasing phantom issues, began creating their own fixes. Some were crude, others ingenious, but all were born from a common reality. The factory wouldn't admit there was a problem, so the field had to solve it themselves. The most common complaints remained the same, so mechanics were replacing parts that tested fine, adjusting settings that wouldn't hold, and throwing rebuild kits at engines that still refused to run right. Gradually, a pattern emerged. The problems weren't mechanical in the traditional sense, they were hydraulic. Specifically, they traced back to the hydraulic tappets. Once people began cutting them open, the mystery unraveled. Inside the tappets, the STC valves were failing silently. Some were gummed up with dirty oil. Others leaked pressure internally, throwing off injector timing by just enough to cause poor combustion. And in engines where all 6 tappets failed at different rates, performance became wildly inconsistent. Shops began offering solutions like modifying or replacing the hydraulic tappets with solid non-STC units. This fixed the idle smoke and made cold starts rougher, but it eliminated the unpredictability. Other mechanics took a middle ground, rebuilding the tappets with tighter tolerances and swapping in updated parts from later Big Cam revisions. Oil cleanliness became another battleground. Some fleets shortened oil change intervals significantly, from longer intervals down to 10,000 or even 7,500 miles, to keep contaminants from damaging the STC internals. Bypass filters were added. Shops began advising against long idle times, recommending warm-up procedures that minimized oil aeration. Another workaround was preventive rebuilding. Fleets familiar with STC issues began pulling heads and overhead components every 200,000 to 300,000 miles, not because the engines had failed, but to catch problems before they started. It was costly, but less expensive than losing powertrains mid-route or chasing ghost issues across multiple shops. In forums and truck stops, the Big Cam's reputation was divided. Some drivers swore it was a problematic engine, full of hidden issues and too sensitive for real-world use. Others claimed it was one of the best engines Cummins ever built, if you knew how to maintain it properly. And that became the real dividing line. It introduced a system most techs weren't trained to service, buried inside a platform that looked like every other NTC. The ones who figured it out became the go-to experts. In the aftermarket world, a few shops became known as Big Cam whisperers, able to diagnose faults by feel, sound, and oil smell. They didn't just fix engines, they understood them. By the late 80s, these workarounds were more than stopgaps. They were the norm. But a shift was coming that would make them obsolete. The era of electronics was on the horizon, and Cummins was already building its replacement. By the late 1980s, the writing was on the wall. With the EPA's stricter emissions mandates, the mechanical injection systems, no matter how clever, could no longer keep pace. Cummins needed a clean break, and it came in the form of the N14. The N14 shared the same 855 cubic inch displacement and much of the basic block architecture as the Big Cam, but it introduced significant changes. The fuel system became fully electronic, and timing, once managed by oil and mechanical means, was now dictated by sensors and a computer. What had once been a mechanically timed system was now precise, predictable, and easily adjustable with a keyboard. For Cummins, it was a necessary evolution. For Big Cam loyalists, it was the end of an era. By the late 80s, after more than a decade and 4 major revisions, the Big Cam was officially retired.